Good afternoon, everybody. Today, our discussion is about the phenomenological modeling of composite detectors. Basically, it's the simplistic view and has been presented on the application of our formalism to composite detectors, which basically consists of a number of encapsulated high purity germanium detectors modules. Here we basically present modified calculations for getting the peak to total and the peak to background ratio of the cluster and spectrometer for integral satellite for the first time, and we consider up to fourfold units. Basically in that field we have a number of empirical method and we also have some sort of simulation. So why do we choose this phenomenological modeling? This is the primordial questions. As we know, there are plenty number of journals or research in that field. Basically, the experimental results and simulated results are easily available in this field. So, a third option is doing some analytical modeling, which is far with some Monte Carlo simulation of this kind of thing. So, this is also a part of simulation, and lots of paper, lots of work is available in internet. But phenomenological modeling is a novel approach, the simple approach. Just here we take the simple concept of probability and use some algebra, some geometry, and we get some outstanding result which is very much akin to the experimental results. So we choose this phenomenological modeling, and our group also did lots of work in this field. Some of the publications we got recently, and lots of work is to be done in that field with this type of modeling in the near future. So our group is basically intend to do this kind of modeling, as it is simple in nature, and also we have lots more to do in the future. So basically what our paper, this publication gives, this basically gives or provide a guidance for designing new composite detectors, and it can also give some important information about the performance of experimental studies with the space spectrometer in the high energy region. Okay. So now the second thing, it's about a short review of our modeling. Basically not on our modeling, but we need these things. The two papers. One is this William et al. And reference theory and et al. Where they did some experiments in a project, and we need some of the results from this paper. And here, as we see, the cluster detectors have the single detector volume of a cluster detector is quite greater in the SPI, and the source to detector distance is also greater, much more greater for SPI spectrometer. Now, as an outcome of our modeling, we obtain the variation of relative efficiency in single detector and add-back modes is quite similar for these two detectors. Just outline. And the second thing is the just is that remarkable remarkable agreement between theoretical and experimental results has been observed for the SPI spectrometer at various energies. Okay. Now, what is our modeling? Basically, our modeling is a probabilistic modeling of a general composite detector. We assume a general composite detector having K modules because we know for cluster K is 7, for SPI spectrometer K is 19, and our group also did some sort of modeling for K equal to 49 or K equal to 5, K equal to this also for a number of for different number of detectors or modules. Okay. And the second thing is all the detector modules are hexagonal and consist of high purity germanium crystal which are identical in their shape, size, and they also placed symmetrically. And now we take N be the portion of the total flux that interacts with the detector module of the composite detector, and obviously of obvious different energies. So now you see when a number of gamma rays just incident on the crystal, what will happen? They have three sorts of probabilities. First one, some of them will get absorbed, some of them after first interaction will be scattered to adjacent detectors, and third possibility is they may be scattered away from the detector without any detection. Okay, so now we take three probability amplitudes for this scenario, which are basically A0 dot, A dot, and Si dot, and from the simple concept of probability we may choose, or we may say that the sum of these three is 1 because total probability is 1. Now the second thing is these were all for first interaction. What will what will happen for second or third interaction? You know, we took for second and third interaction all those probability amplitudes remain same, but the value of these parameters or amplitudes will be different from the first one, and we took it as a primal tool for our modeling, and we saw that this is correct to some extent or to some energies, basically up to 8 mm or 10 mm, roughly speaking. And these three probability amplitude will also add to get the same result of 1. Okay. Now, this is basically an idea which I am giving about Clover detector. Here in this paper we exclude Clover because it's our previous publication, but one newcomer or to understand the cluster and the SPI spectrometer, one should know what is Clover. Basically, Clover is coaxial germanium detectors just arranged like 4 leaf in a single cryostat, which is in 77 K in the temperature. Okay. Now we have different types of clovers. In NaCl there is Sega clover. This is in Triumph. This is Tigris clover. It is minimal at sun. It is exogam in genil, and this is grey patrician. Okay, and this is the front view of 2 leaf. Now again we start our modeling. What actually we did is basically a probabilistic modeling. It's a schematic diagram of cluster detectors, and it is the schematic diagram of SPI spectrometer. So, cluster detectors consist of 7 adjacent crystals, 6 adjacent crystals, and 1 central detector. And the SPI consists of a number of modules, basically 19 modules, where there is also one central detector. Now the pattern of scattering is basically has some difference. Just you see, for central detector, when a gamma ray interacts with it, it can have the possibility to scatter away to the 6 adjacent detectors. So these are the possibilities, 6 possibilities. And for this, just you see, there is also 6 possibilities. Of them, these 3 possibilities, we can neglect these 3 possibilities because they are scattered out the detector. So we took only these 3 scattering, which can give some sort of absorption inside the detector. Okay, so as we see here, there are only 2 modules. Nice. And here there are 4 types of modules. Nice. Now the second thing is again the probability amplitudes. So for here, for this we took this SIO, this SO, A, SIO and SO. These are basically important for naming. And for central one, this is for C because this is the outward. So SIO, this is SIC. But it is worth noting that the absorption probability remains same. Now one thing, okay, I will say it later. Now just to see, for outer detectors, what will happen? Just 6 n number of gamma rays are incidentally on the front face of 6 detectors. So total events after second interaction will be this. Okay. But we know this SIO is like this. So we put it here, and this term also put it here, and after substitution we get, after third interaction, the total events will be this, and after fourth interaction these are the total events. Okay, let it be clear in this for the central detector, because here only a single detector, so there is an easiness. Just to see, for central detector what happened, NC is the total events for first interaction. So it has 3 parts. One is absorption part, the second one is the scattered away to the adjacent detector parts, and the third part is, the rest part is scattered away without detecting. So this part basically has no importance. Now after second interaction, what will happen? Basically we take care for third interaction. What will happen? We put all these terms in, and after fourth interaction also we got these are the total absorption terms or absorption events. Okay. Now there is a twist. We have SIC, SIU, all these things, but we have to consider all the probability amplitude in terms of those 6 probability amplitudes. That means SI prime, S0 prime, and A prime, and A, and SI, and SO. So from the diagrammatic picture, from the scattering situation, we have to determine what's the value of this SIC prime, or all these things. These are the same because these things are same. But for outer detectors, just to see, a dot is a dot, but SI prime is half SI prime. Why? Just to see the picture. Just to see, there are 6 possibilities. When a gamma interact on it, there are 6 possibilities, 3 these and 3 these. But these 3 possibilities we cut it because they do not contribute with absorption events. Okay, so we have 6 possibilities and we have absorption possibilities, there are 3. So the probability 3 by 6 means half. Okay, so we get this as half is I prime. And in the same scenario, if we just think in the same way, then we get these are the probability amplitudes for each outer detector. So as a result, we got total number of events after fourth interaction is this, where this alpha cluster is the manifold events term, and this is basically equal to this term. So now SPI. What will happen to SPI? SPI have 19 detectors. So there are four groups of modules, and we define those as A, B, C, and D. And we see here this is the distribution of scattered events. This is basically 2/3 B and 1/3 C. Just to see here, because this A equal to 6. What is A? Just to see, this is A. So this is A. So for A, what will happen? The 2/3 of the possibilities will get absorbed just with B, because this is B, and 1/3 has the possibility to get absorbed with in C. So we get 2/3 B plus 1/3 C. And what will be SI? Because SIA is equal to SIA, there will be some absorption, and is 2/3 and 1/3. So we take 1/3. So this is SIB and SIC. In the same manner, we can demonstrate all these four, and we ultimately what we are want to getting from this, we are wanting to get this is SPI spectrometer could be considered to consist of four group of detector modules. The details for each case we have shown earlier in the table. Now what we do? We actually do calculate and show the expressions for scattering probability to the adjacent modules. And now the thing comes, what will be the total events or total counts? Now, as I said, for cluster detector, here also Na, Nb, Nc and Nd represents the gamma flux intelligent module of types AB and C and D. Now Na is equal to 6n, because A type of module, A group of module consists of 6 single detectors. Similarly Nb and Nc also, and Nd is single. This is the central one. In the same situation, we get the total counts for A type of modules is this, and after third interaction this will be like this, and after fourth interaction is this. In the same manner, we got after fourth interaction the total for B module, for C module and for D module, and we got all this here. Then also we said earlier, because we have SIC, SIB, but we have to transfer, or we have to think all these probability amplitude in terms of those 6 probability amplitude. So in the same situation, we got these are the 6 probability amplitudes for type A, and these are for type B, and this is for type C and D. So the total events in that case is this. Here also we have alpha SPI, there was alpha cluster, and alpha SPI is equal to this. This is basically multiple hit events. Okay. Now, what are the results, or what we actually got from our modeling? This is performance parameters. Okay, because a detector, it would be good, it would have some moderate performance, but you should know the performance parameters, that is peak to total ratio, peak to background ratios, some full energy peak events. Okay, but in our modeling, basically we calculate peak to total and peak to background ratios, because full energy peak efficiency calculation is quite impossible for it. So this is the peak to total, because Kn is the total events. You know there are n gamma rays and k modules. So total events are Kn, and this is the absorbed events. Okay, so peak to total is basically A prime plus alpha. This alpha is alpha cluster to cluster detector, alpha ASPI for SPI detectors, or for different detectors we can say alpha proba this kind of thing. And this, what is the TS? Here we take some suppression. What is suppression? Basically we said there is a chance to scatter away some of the gamma rays out of the detector. So we have no scope to count those events. But if we give some suppression, it may be compensated or anti-compensated or some kind of thing, then you have some suppression. So experimentally suppression is possible, and we define some parameter which is suppression parameter or suppression factor, which is kappa. So if we consider this kappa, so total events become this. So this Kn will become this. Okay. So peak to total and peak to background ratio for suppressed detector will also like this. Okay. But here you keep in mind that for single detector mode alpha is 0, because alpha is for multiple heat events. Multiple in that sense, multiple heat within several detectors, within just adjacent detectors or nearest neighbor detectors. But for single detector mode, there is no alpha. Nice. Now this is our approximate values of the detector heat ratios and the relative efficiencies in add-back mode and an add-back factor F for 3 gamma energies of cluster detector. Okay, so these are empirical, these are experimental values. But basically, what we did, you see, here is A prime. Calculate it. We have some calculations which I show here. There is some calculation. We calculate A prime as this for these energies, and alpha cluster is equal to this, alpha is by this, and we just calculate these two parameters like this and plot those. What happened there? Just to see, for suppressed case, we took kappa equal to 0.5. That means half suppression. The half of the event that scattered out of the detector without any detection would be added to the recorded events. Okay. So now what will happen? This ping for add-back mode for the SPI and this add-back mode for the cluster. So what will happen? You see, this is peak to background ratio. This is the energy, and this is these two are the terms. Nice. And here these two are the terms. Nice. And these are what? They are for add-back mode for the cluster and this single detector mode. As we know, for single detector mode the value will be less. Okay, so there will be no confusion. So it has a decreasing trend. Okay, I will discuss in the later slide. But here see, when suppression you want means full suppression, at that time peak to total become 1 because it is theoretically correct, and the solid one is for ASPI spectrometer at 1.3 MeV, and this is 8 MeV. Just you see, in less energy regime suppression is also good, and peak to total ratio is also greater, because this is the real life situation. When your ancient gamma replace energy, it would be absorbed easily. Okay, now we see the comparison. Basically, what have within this peak to total and peak to background ratio? What we observe, the values of 3 quantities are essential for determining the peak to total and peak to background ratio. As already we have said, 4 quantities. Here alpha, this is n, this is not n, alpha, kappa, and your R1, R12, and add-back factor. Okay. So even if the values of some probability amplitudes remain unknown, we have some chance to extract the values of the peak to total and peak to background ratio in indirect method. Okay. Now a third situation may be arise. We can extract FEP related information for energy, means full energy peak, which is basically an experimental performance parameter. But we can extract a FEP related information also in terms of peak to total and peak to background ratio. Okay? And then another important thing is the peak to total and peak to background ratio have been calculated as a function of gamma energy. Just as you saw in the diagram, in the graph, that both ratios show a decreasing trend with higher energy. I just told that it is very common because in high energy regime there is much more scattering and a chance of getting out maximum of the energy in gamma ray out of the detector without any detection. Okay. Again, there is another thing. What happens if we take kappa equal to 0.05? Then what happens? Peak to total and peak to background ratios have been calculated as a function of gamma energy, and is shown in the result. There is a decreasing trend, and the trend is similar for different modes of operation. It is very interesting. For different modes of operation, we have much more modes, but the trend is same. The trend is similar. There is no change in the trend. Okay. The second thing is in adiabatic case. In adiabatic with suppression case, peak to total ratio for different energy we calculated, shown in the figure, and we see there that is for kappa 1, peak to total is 1. So theoretically it is correct. Okay. As our summary, just in short, we say this is basically a probabilistic model based on the absorption and scattering of gamma rays. We can understand the operation of cluster and SPI detectors. Okay. In our formalism, the operation of these sophisticated detectors could also be explained in terms of 6 probability and amplitude. We can adapt up to 4th interaction. We may do for the higher step, but basically the contribution to FEP for the higher order interaction is very much less, so we are not interested in that case. But if we choose very high energy, so maybe added up. Okay. The third thing is very important thing. Results indicate improved performance of the SPI spectrometer compared to cluster detector in the adiabatic mode. And another thing very much important is for high energy gamma ray source. Just as we know, it's very common problem to get some high energy monoenergetic gamma ray source. So if we didn't have high energy gamma ray source, let's say just 8 MeV, again we have some indirect way to calculate all the performance parameters through our modeling. It's a very much it's a good achievement for us. Okay. And the last thing is our modeling can give some guidance to formulate any simulation scenario or to set up some experiment. This give some guidance for future simulations simulations or experiments, because you could get a good roadmap. What will happen after that energy? What will happen after 4th or 5th interaction? What will happen after several heat events? Okay, we can get some view, some overview of all these things. So it's very important tool. It's very important tool for future for establishing different even experimental situations, or just to develop some simulation scenario. as I said earlier. So this is all about our this paper, okay, and about just this cluster detectors and SPI detectors modeling. Okay, so one can have some questions that which paper just we are talking about. So I'm showing this. Just wait for 1 minute. So this is the paper which I'm just about which I am talking. Okay. Paper is just I'm showing 1 minute. This is the paper. Okay. What I'm talking about. This is the paper published in Phenomenological. Okay, so thanks to all for watching.